t. Where's that? Oh, that's there. Okay. That'll work. Oh, this is so exciting. All right. Can anybody tell me one of the distributions that we've learned about? Any distribution, guys? Can anyone tell me the name of a distribution we've learned about? All right, there's one. Normal distribution. Give me another one. Somebody else. Binomial. Kick ass. There's one recently we learned about related to waiting for a bus.
Discrete population.
Okay. So a discrete type. Yeah. So discrete would be like a binomial. Continuous would be like the big branch and big umbrella covering everything. So a normal is an example of continuous.
Discrete.
And discrete would be like a binomial. I like it.
Yes.
There's another continuous one we learned, and the specific example we did was waiting for a bus. If I'm a cop, I'm going to wear a badge. No, but I'm going to wear a uniform. So it's uniform distribution. So when you see this question, describe the distribution of x, and it's got this here. You can either put a B here for binomial, a U for uniform, or an N for normal. So that's the button. Yes?
Would you not do like skewed there?
No. Skewed is not a general distribution that we know formulas for. Skewed is just a condition that something can happen. There are distributions that are skewed. So here, so it could be binomial, uniform, or normal. This one is what kind? This is problem about rolling a die and seeing and trying to get a 1. Yeah, because what could you get? You could get a 1 or not a 1. There's 2 things you can get. So that's binomial. There's a P, there's a Q, that is completely binomial.
So how can you tell the difference between binomial, uniform,
Uniform is going to have to say it's uniformly distributed. They're actually going to have to say
okay.
it. That's the only way I would know it. Or they might give me a picture where it's a perfect big rectangle. That's uniform, yeah. Normal, of course. Now, let me ask you this. What was the most important stuff we figured out here? I love it. And in fact, isn't P more important? Because whatever P is, then I know what Q is, correct?
Yes.
So the 2 most important things for me to know when it's binomial are N and P. So what's going to go in here is N and P. So you're going to put N and P. So in chapter 6, they're going to say we have a normal distribution, and the mean is 11, and the standard deviation is 2. Then you would say X follows a normal distribution. The mean is 11. The standard deviation is 2. Because for a normal curve, the most important things to know are the center and the spread. So this is this book's notation. You will not see this anywhere else, right? But this is kind of interesting. They just say, what's the most important things? What kind of distribution is it? And what are the 2 most important things? Now, what do you guys think about uniform? I know we just got into it last time, but what's the most important thing for me to know about a uniform distribution?
Obviously where the line actually lies.
Yeah, so it would actually be, if I call this A and I call this B, those are most important. Where does it start? Where does it end? So remember the bus problem I did, it was 0 minutes to 15 minutes, which actually told me how tall it was. So those 2 are the most important things to know for a uniform distribution. So you're going to see this question, and again, an example of it is 94C in chapter 4. You're going to see this question with a little blank and then followed with parentheses. It could either be binomial with NP, it could be normal with mu sigma, or it could be uniform with AB where it starts, where it ends. In each case, it's just what are you working with and what are the 2 things that you know that's the most important things. that's 94. A little bit of help for you for 94 in chapter 4. Any other questions? And let me see, what was? Oh. What was the last handout?
You talking about the one we did last time?
Yeah, I was gonna see if anybody needed that. That was the one about the uniform. Did I give one out about uniform? No. Okay, good. I haven't given it out yet. I think- No, that's
Oh yeah, the different numbers.
yeah. No, the one I'm talking about I haven't given you yet. I've got it up here.
Oh, okay.
I was afraid I already gave a copy of that. Daisy. All right, guys. Any other questions from homework? Sorry. No. Is homework going okay? You guys are maybe no. I'm sorry. You guys have any fun plans for spring break?
So,
Yeah.
No, I'm sorry.
My sister's having a wedding shower.
Oh, dude. All right. Well, congratulations to your sister.
Wedding shower.
Nice.
Not me, it's not mine, but.
No, well, I would hope.
well, for your
I
sister.
really would hope.
Yeah, she lives in the Midwest.
I won't judge, but that would be TMI. Okay. Is it warm enough here, guys? Tell me. Yeah, it's definitely warm enough for me. So I'm gonna turn this sucker off. All right, turn it off. There we go. No. There. Okay. Well, let me know if it gets cold, because I normally run hot, so I'm not gonna notice too much if it gets too cold. Yeah.
Well, I got a laptop yesterday.
Okay.
Yeah, easier for me now to do homework at home now.
Kick ass.
I know.
All right. It's crazy. I still remember. Anyway, kids. I'm old, so I remember when the internet first came out,
Yeah.
and we were, dude. First days of the internet, you would click a link for a website, you would walk away.
You wait for it to go on.
You'd walk away, and you'd do some other stuff. You come back, all right, and you go somewhere else, and you come back, and the page is loaded. Click a link. Okay, let's go do something. Oh boy. Anyway, sorry. That's enough of that. Yes.
I don't want to reminisce too much on old technology, but it's also by my understanding that something completely lost in our generation is having to pause your conversation whenever a plane goes over.
Oh,
If you remember doing that,
sure.
because they've just gotten way quieter.
Oh, well, they still. If you've ever been to the Starlight Theater, which is in Balboa Park, the last time I went, they still did it. When the plane went overhead, everybody pauses on the stage, which I think is neat. And I went and saw My Fair Lady. You guys ever heard My Fair Lady? That's where the rain in Spain falls mainly on the plane, right? No? Okay, look it up. So the plane went over, and the guy changed his line to be something about the planes going overhead. But so that's kind of funny. Anyway. Okay, sorry. Enough of that. All right, I love it. I can see in your eyes, you're all like, "Good Lord, what are you talking about?" Okay. So if there's no questions on any more homework stuff, then we're going to get right back into where we left off. If I remember correctly, we had just done like one uniform probability example, if I remember correctly. So today what I've got like a worksheet where you can practice the binomial and the uniform. And let me just say this, what's happening next week? So the Wednesday we come back, which I can't remember what date that is now. But
You mean Tuesday?
oh yeah, today's the Thursday of the first week we're back. I teach a Monday, Wednesday class, so I'm always like forgetting which day. So Thursday that we get back, whatever day that is, right? The first week we're back, we're gonna have a quiz on chapter 4 and 5. So I'm not going to quiz you on the first day that we're back. I'm going to quiz you on the second. And my other class, they actually have a test on that Wednesday. Right? I'm not an asshole enough to give a test on the Monday after spring break. I'm not that big of an ass. I have had a teacher do that to me as a student. So I know how it feels, so I'm not going to do it anyway. Okay. So let's try a uniform probability problem. And then I want to show you, does anyone remember, real quick, kind of rundown of some things here. If I just give you a list of data, then you can figure out the mean, and you can figure out the standard deviation. Let me stop for a minute, I really want that. Right, if I give you just a list of data, we figured out how to get the center of the data. The mean is the most commonly used center of data. We talked about why sometimes the median is better, right? And then we also figured out how to calculate the spread of the data, which is really important to me as a teacher, because when I analyze test grades and quiz grades, I want to know what the average is, but I also want to know what the spread was, right? If the average was a 70, but the spread is 20, that means that there were people that made maybe hundreds, but there are also people that made 30s. And that's why it's so spread out. Whereas if the average is 70, but the spread is 5, then most people clustered around 70 for some reason. And it's good for me to kind of see that, because not many people made A's then in the second one, right? So these are two very important numbers to calculate given a set of data. So one way I can give you data is just a list. The second way we looked at how to give data is in this kind of format. And who remembers what the mean formula was for this? Anybody? Remember what we had to do when I give you lists like this? You have to make a third list.
Oh, it's
Yeah. In fact, another name for mean is expected value. And what does it look like the first three letters are here? It's kind of nifty. We didn't do that because of that. It's just an interesting coincidence. So the mean is also called expected value, and the first three letters look like EXP. Okay. Again, just a coincidence, right? And what was the standard deviation for this? This is a little bit more involved. It's where we had to do another column after XP of X. This is the one where we had to use a little algebra to kind of see how it could become that. It just makes it easier to use the lists in the calculator to get all the numbers we need, right? But then, and I've said this a few times, every time you get data in some way, we have to figure out, okay, in this way, is there a quick way to get the mean? Is there a quick way to get standard deviation? So when I'm given like this, I could make a list, but very often that list could be thousands long. So I'd much rather use these shortcut methods to figure out the two most important numbers, the center of the data and the spread. And then we got a binomial business, right? We got NPQX. This mean is kick-ass. Anybody remember the mean for binomial? It's really tiny, beautiful formula. NP. And I could explain to you why that's true. This one would take a little more mathematics to be able to explain it, but anybody remember what that formula was for the standard deviation? So every time I'm given a different type of distribution, the very first thing I want to do is, how do I get the two most important numbers? The mean and the standard deviation. Is there a shortcut way to get those numbers given that I have this distribution? Right. So for the most simple distribution on a list, the formulas look a little gross. For what's effectively another kind of list, the formulas look a little bit gross, but a little better. And then for this guy, which is just sort of an idea, the binomial probability, the best formulas yet. Right? There's no sums to do, there's no lists to make, kicks so much ass. So, we just learned a new distribution. Uniform distribution. So I want to do a little review of uniform, and then I want to talk about what its mean and its standard deviation is. And just to kind of tell you, I almost sometimes don't want to say this too early, but I'll just tell you right now, I'm not going to use those formulas very often. You're going to see them in the homework. I want you to know those formulas exist, but I'm not going to put them on a test or something. They're really not as important as some other things, but you will see them in homework. Okay. So let's review uniform. I'll show you the mean and the standard deviation, and then I'll finally shut up and let you guys try some problems together on this worksheet. So let's say, all right, just to make it easy on me, I like it. If I ask you how old you are, and you say 25, couldn't you be more specific?
Yeah.
So is age continuous or discrete? Continuous. Otherwise, when your birthday, you actually would age a full year just all of a sudden. It's my birthday, you know, and you would age. No, that's not how it works. Yes, we age continuously. So when you're really young, you wouldn't say that you're 3. You would say that you're 3.5, right? When you get older, you don't say, I'm 50.5. No, who are you? What are you talking about? You guys semi with me? So we sort of drop it, but still it's continuous. So what if I had a situation where there was a uniform spread of ages somewhere in a elementary school or something. So it's anywhere from 5 years old to, 11. A certain school teaches these grades, right? And I know it's uniform. They must tell me that it's uniform. There's nothing I can calculate that'll tell me. They have to tell me it's uniform. There's nothing I can kind of figure out by myself. Do you guys remember what shape a uniform distribution takes? That's weird. Oh, I see. That's there. Okay. Big ass rectangle. In fact, that's the idea of uniform. In fact, the word uniform is reminiscent, like I said, of a cop or a mailman or something. Uniform meaning the same, right? So uniform probability distribution means everybody gets the same probability. Okay, I like it. So 5 to 1. Can somebody figure out, do you guys remember, how do I figure out the height of this rectangle? What must be true for this picture to represent probabilities? So we talked about the dartboard last time. I want the whole thing. If I add up all the probabilities in a situation, what does it have to come out to be? 1. So if I make the area of the whole shape 1, then the probabilities of any pieces of it will just be the area of those pieces. That's almost too nice to believe. Right? And I've got an example to kind of show that even better. Guys, off the phones. What's up? Okay. So, does somebody remember, how do I make the height of this? I need this area to be 1. So how wide is it at the moment? What's this? 6? I know what you're thinking, but it's 6. Yeah. And then how tall does it have to be so that the total area is 1? What do I multiply something by to make the answer 1? I multiply by its reciprocal. So this will be 1/6. I like it. So if I pick randomly one kid, what's the probability that kid is 3.5 to, not 3.5, let's not start there, 7.5 to 9.5 years old? can you draw that inside this? What would that look like? So I got 7.5, and I got 9.5, right? So then it looks like this. And again, this is a lot like that dartboard, and if I want to get the bullseye, that's the area I'm talking about. So what percentage of the whole thing is that piece? Same idea here, it's almost too nice to believe. This is the visual of my question. The answer is going to be its area. So how wide is this red rectangle? 2. And how tall is it, of course?
1/6.
Everything in here is 1/6 tall. So it's got a 1/3 chance with that. So uniform probabilities are freaking awesome because their shape is so simple. It's just a bunch of rectangles. Okay. So you guys try this problem. So this is part A. You guys try, what's the probability that a kid is somewhere between 5.6, now we're getting really specific, I love it, up to 9.9 years old. Something you don't hear very often. How old are you, kid? I'm 2.73 years old. Holy shit. Every question lives inside the original thing. For some reason, I have people that change the height based on the question. Can I change the probability of something happening by asking a question? Well, the probability is you probably ask a question. But I'm talking about like the probability that a meteor strikes the Earth. If I ask a question, hey, will a meteor strike? And it's not going to suddenly be a meteor. So I'm not going to increase or decrease the probability it's going to hit the Earth. Yes. So for some reason, people take the question and they make a new picture. No. Everything's living in this whole thing. So the only thing you have to worry about that, once you got this set up from the beginning, once you got this figured out, the height, then it's just figuring out one thing, really. The width of the question. How wide is that? 4.3. So then the probability would be the width times the height. I love it. And whatever the hell that is.
0.7166.
0.716 forever?
Yeah.
Okay. I like it. And if you wanted to, you can make it 71.6%. Well, it's up to you. I'll take it either way. Okay, not too bad, right? Uniform probability distributions are beautiful. They're crazy. So let me see what you guys think about this question. What is the mean? What's the mean of this distribution? Yes?
8.
How do you get that?
Because since everything's the same probability, you just pick the midpoint.
Exactly. You have all the same amount of each data point. So it's just going to really be the average of the output, the extremes. 5 plus 11 divided by 2, 8. Or you can just find a number that's in the middle. 3 over, that's 8. That's kind of nice. The formula for the mean of a uniform probability is just add the ends divided by 2. That's crazy. Now here's gonna come, no, okay. Let me see if this happens. Here's the formula. So remember, this is A, this is B. So in general, the formula for the mean of a uniform distribution is A plus B divided by 2. That's the formula.
Yeah. You know, C is that where it says 5 plus 11? Is that a 2 or 8 on any?
Oh, I'm sorry, dude. Yeah, that's a 2.
Oh, okay. Thank you.
Yeah, please ask me. I had a teacher once, I know I write horribly. I don't know if you guys have noticed. But I had a teacher that wrote so horribly. He would say, hey, what did you write on that first line? And he would say, does anyone remember what I wrote? He couldn't read his own writing, so you need to retire. So please, that's another 2 there. The standard deviation, let me just write the formula down. And again, if you've taken calculus, you could actually derive this formula. You don't suddenly have to know calculus. I'm just going to give it to you. And let me see what your reaction is.
Interesting.
Okay, I like that reaction. It's bigger on the inside. No. Yes?
I was trying to think if there, because I feel like there's a very straightforward way of doing that.
Not really. There's a couple ways to do it. One of them's more straightforward.
Yeah.
But again, if you know enough math, then it is relatively straightforward.
Because it's like, wouldn't you want just to have the difference between the max value and the mean divided by 2? Or would that be wrong?
Wait, the difference between?
One of the extreme values and the mean divided by 2.
Oh.
So the midway between the mean and.
I see. It's a little over, that's too simplistic. That wouldn't really get you here though, would it?
No.
No. So you're proposing a different formula for it.
But then I'm guessing that would probably be wrong in
Yeah,
some scenario.
yeah, it's too simplistic. Normally when I put that up there, the very first thing people say is, does anyone else have any reaction to that formula?
Where'd you get the 12?
There it is, that's what I hear, right? Why the 12? Okay, so what I did before, and what I'll do again, is I'll put on canvas the proof of this. And if you wanna look at it, you can, and if you never wanna look at it, you don't need to, right? Because I'm sure some of you guys are like, just tell me where to put shit, right? But I hope some of you guys are curious, why the shit is it a 12? I mean, that's really, why the shit is it anything like that, but especially the freaking 12, right? Okay, so hopefully I remember to do that. I got the little proof written up, so I can put that up there. So in this case, the standard deviation will be the square root of b minus a squared over 12. So I get the square root of 36 divided by 12 is 3. The square root of 3 is like 1.7 something. I feel like I should have it memorized, but oh well.
Would we just put rad 3 or would we round it to 4 decimal places?
Oh, I see what you mean. Yeah, if you have to do stuff with it, you should round it. Yeah. What'd you get? Oh.
Sorry.
No worries.
1.7320.
Okay, I like it. Kick ass. So in the homework, there will be maybe a couple problems where you actually have to use these formulas. I don't, and again, I always get in trouble when I do this. I'm not gonna put it on a quiz or test. It's not as important as some other stuff, but in the homework, you will need to do this. You can just plug stuff in the formula, no big deal, because I want you to realize, whenever I get any distribution, I wanna know how to calculate those two things. So there should be a way to calculate those two things, and there it is. All right. Let me ask you one more question about this. Maybe 2. Looking back at this, what's the probability that I pick a kid who is older than 11?
0.
You guys agree? Every kid is from 5 to 11. So what's probably I pick a kid who's older than 11? No chance. What's the probability I pick a kid that's from 5 to 11? %, chance, right? 1. You will see questions like that in the homework. Let them be simple. It's just the area. So this is really saying, what's the area of the whole thing? 1. This one's saying, what's the area in a place where there is no height? 0. And then I lied. I got one more question. What's the probability that x equals 4? I'm sorry. I keep thinking it starts at 3. X equals 10. There we go. Remind me, when I'm given a continuous picture, the probability is the same as the area. So x equals 10. That's right here, roughly, right? What's the area of that? How wide is it?
I think because if it's a continuous thing and you're saying 10, that just meaning 10 dot 0, 0, 0, 0, like infinite, then wouldn't it be like infinitely like thin slice?
Sure, you can talk about sort of related calculus, you can go infinitesimals, you can talk about dx, whatever, but that's basically the limit of that is 0. So what's the width of this? 0. What's the width of any line? 0. It's got 0 width. So what's the area of this?
0.
0. So to really make this make sense. Oh, it's that? Okay. So if I said I'm going to pick a number from 0 to 1, is everybody cool with that, by the way, what I just said? You guys understand? So what number could I pick then?
0.5.
There we go, thank you. Or 0.4973332 forever, right? That's a valid number. Stay with me. How many numbers are from 0 to 1? There's an infinite number of numbers, yes? So the probability of any one of them will be out of infinity, which is basically 0, right? Now, towards your point, the probability of each one can't be 0 really, because if you add them all up, it's supposed to be 100%. So for us, for most humans, the answer to this question will be 0, because it has 0 area. For math people, the answer would be what's called iota, which is the smallest positive number. It's just the name we give this idea. It's an idea, it's not a real thing. But that's going too far, sorry. I see some of you guys like, okay, whatever. Okay, but just in case you're curious. Have any of you guys ever heard the word iota being used at all? Iota?
I've heard the word.
Okay. Sometimes they talk about like you have an iota chance of doing this. Sometimes, so it's not a very common. Okay, I'll stop. So uniform distributions, let them be nice. It's just finding areas of rectangles. Almost too good to believe. If you just draw the picture, figure out the height based on how wide this is, you're golden. Do you see why somebody might put 1 over 11 here?
Yeah.
Because they focus too much on that number there, right? But it's got to be based on how wide this is. So, I want you guys, there's two sides. I want you to do the side that does not have the hills on it, the normal distribution. We're going to do that later. I want you to do the side here, binomial and uniform distribution practice. Okay. If you need to borrow a calculator, wait until I get back up there. I can give you one. Let you borrow one. Yeah, the shoes are funky. What kind of shoes are those? Dude, sorry. I've never seen that. Thank you. Sure. All right, this works out. Let's see. Oh, yeah, sure.
My driver's license, sir.
No way. I'm okay.
I don't know what you're doing.
All right, let me see. I do kind of want you guys working together on this, so I know you just love it so much when we do that. Gonna get you to do groups of 3. So, like maybe you 3 right here, right? Nico, you want to go back, work with those 2 back here?
All right.
Yeah? And then you 3 right here? If you would kind of like be close to each other. Thank you. And just help each other out with whatever makes sense to you. Help the other people out. Alright guys, I'm gonna try to catch up.
Similar but different.
Actually, no. We're like three. But, okay, the reason I didn't show.
Oh, okay, I see what you mean.
I had to write the speech. I submitted it around 5:30. So I'm like,
Oh, so everything's similar,
So,
like,
I'm like,
this one. Each one is
Like,
like,
okay, I'm like,
Yeah.
so it's like 0,
So I think that was the class, and I didn't go to next class.
Oh,
Alright guys,
So
so
my third.
binomial probabilities are pretty straightforward to spot. They're gonna give you a probability of something happening, and then you talk about a certain group of people. So that's already N and P, and then you can calculate Q. So there's a certain look to a binomial probability problem. So across all of mathematics, the hardest thing to figure out is when do I do what? So very often students are like, I know how to do that, I just know when to do that. So it's all about identifying the situation you're in, right? So binomial probabilities have a certain feel to them. There's a probability of something, which means there's a probability of not that thing. There's a group of people you're talking about, and then you want to know the probability that some of them do the thing. That's telling you it's a binomial. If I see it's binomial, there's three things I want to know right off the bat. What's N, what's P, what's Q? Holy shit, Joe. So in this case, N, of course, is 26. It always means the size of the group we're looking at. P would be 0.23 because we're looking for satisfied, so 0.23, and Q's got to be the rest. So P plus Q is always 1, because together they make everything, satisfied, not satisfied, that's everybody. And then you throw it in, and of course, realizing that a lot of equations can be read as a sentence. 26 people, choose 5 of them to succeed, so that means I got 5 of those, and the rest are those. 5 successes, the rest are failures. And I think everybody I looked at got, is that right? Is that one?
Yeah.
1750. Kick ass. This one, probably x greater than 2, is equal to 1 minus the probability 0, 1, or 2. So the very first thing I want to do is figure out the probability of 0, probably 1, probably 2. Oh, let's see, so if I do the probability of 0, that's 26, choose 0. So I got no successes, and I got all failures. Good bad. So that by itself is 0.0011. So what do you guys got? Anybody? Yep.
Yep.
And then I could just do this, bring that back, and just kind of make it 25, 1, 1. So now that's choose 1. Now that's 1 success. 0.0. Where'd it go? 0.87. And then 2. So that would be 24 because this is 2 now. I don't know why I put those parentheses, by the way. So I want that to be 2. Now I want to choose 2, so I get 2 successes. The rest are failures. I get this. Let's see there. So if I add those up, I get 0.0422. So then 1 minus that, I just answered the opposite question. So the person asking is like, what the shit, answer my question. And then you 1 minus, there you go, buddy. There's the answer. So that's 0.9578. Is that what you guys got? Mm-hmm. Now real quick, just to remind you guys, here's a way you can check your work. You're gonna have to show me your work. But here's to remind you, here's how you check it. You would go to distributions, above vars, it says distributions. Go to binomial. If I do binomial CDF, that means it's going to go from 0 to whatever I plug in. So I got 26, I got 0.23, and I want to go up to 2. That's what I'm doing here. From 0 to 2. Let's see if it gets about 0.0422. Oh, holy shit, right? That rounds to 0.043, because I rounded on the way, but that's still a good way to check that you're on the right track. Let me stop for a minute, are you guys? And again, if you don't want to do this on the calculator, don't. You did the problem. This is just to check it. Okay, maybe. Calculator costs enough money, it should be able to do it, and it can. So you can check your work. Part C should have been kick-ass good, because what's the mean? What's the formula? N times P, so that's awesome. 26 times 0.23. What do you guys get for that?
5.98.
I love it. So the mean is about 6 roughly. Standard deviation square root of NPQ. And what do you guys get for that?
In total?
Yeah, what's the answer for the standard deviation?
2.1558.
Yes, 2.14, we'll make it 146. So always round the standard deviation to at least 3 places. So if you want to go more, 3 places. So if you want to go more places, feel free. In fact, let me say this. If you just round everything in this class to 4 decimal places, there will be one exception to that, and you'll see why. Then you're covered. Standard deviation has to be at least 3 places, yes? Probability has to be 4 places. So you can just round everything to 4 decimal places, and you're covered. Does that make sense? If you want to, it's up to you. Okay. More is good, less is bad. So, would it be unusual to find 8? Well, let me build what usual is. The mean is 5.98. If I go up 2 steps and down 2 steps, that tells me where things should normally be. So if I add 2 of these, what's that, 4.28 roughly? So that would be 10.26 roughly, is that right? Nobody's gonna help me? Okay. And then that's 4.29 roughly, so that would be 1.69 roughly, I think, if I'm doing that right. I don't know if anybody got to this problem yet. So basically you put the mean in the middle, you go up 2 steps, and you go down 2 steps. And when I say step, I mean standard deviation. I think a standard deviation is steps that I can take. So normally, I would get between those things. That would be what I would expect to usually happen. So is 8 unusual? Is 8 outside of this? Where is 8? Like right there, so no. Not unusual, it's not far enough away from the average. So would it be unusual to find some dude that's 5'10"? Would that be unusual if you saw somebody who's 5'10"? No, you wouldn't give it a second thought. What if you found some dude that's 7'3"? Is that unusual? Because it's so freaking far away from the average. So this is just a way to make far away more formal. What the shit's far away? More than 2 standard deviations either direction. That's far away. So if I saw a 4'1" dude, unusual. 7'3" dude, unusual, because it's so far away from the average. Okay, I like it. That's almost too nice to believe. That makes a lot of sense why we call that unusual. It's a formal definition. Okay, and I think most people did number 2 first, but let's do this. So when I draw this, it's got to look like a big rectangle from 22 to 39. So there's the picture, and it's not complete unless you indicate the height. So what's the height of that?
117.
Yeah, this is 17 across, so it's got to be 1/17. So more than 28 minutes. You don't have to redraw this every time. More than 28, so it's from 28. And let me shade that in. So now I just got to figure out the area of what I just shaded. That's it. Uniform probability problems are like so beautiful. So how do I figure out the area of this rectangle? Well, what's the width? 11. So 11 times 1/17. And whatever the hell that is. What is 11 divided by 17? 0.471. Just under a 65% chance that a student has to wait, that it takes them more than 28 minutes to finish the quiz. What about less than 22 minutes? Why is that easy? Nobody finishes less than 22 minutes for whatever reason. So 0% chance. And this one is 0 for two reasons. X equals anything would be a 0% chance because it doesn't have any area. But especially for 8, which is way the shit down there. So I don't know why I made it 8. But it's got a 0% chance twice over. Okay, maybe. So last thing for today. Last thing for today. Let me leave this up for a bit. Did I start you over again? Probably not. No, I did. Holy shit. Okay. So what we're gonna do, oh, yeah, that's true. Let me do it this way. I don't have a ton of time, but oh well. Alright, this could get interesting. Alright, we'll see how this goes. It's not really, we're gonna work on this together. That's what we're working up to. Oh, so it kind of shows a weird way to print these out, but oh well. So I'm kind of going to go through this. I'm not going to go through every detail here, but I want to get the idea across. So up here, just to kind of do this a little quickly, flip a coin, and I'm going to flip it 14 times. So it's 14 times I'm going to flip it. The probability of a head is 50%. The probability of a tail is 50%. So if I wanted to probably get exactly 9 heads, 14 flips choose 9 to be heads. So we've got 9 successes and 5 failures, right? If you plug that in the old calculator, let's see what we get. Is it 9? 5 to the 9th. I'm going to do it the long way, but some of you guys might see a shortcut here since they're both 0.5. So I get 0.1222, right?
Yes.
Do you notice down here in this little table here, look at 9, 0.1222, or 122, it actually just goes 3 places because it's not as good as us. Just to show you what this table is going to represent. If I want to get at least 1 head, that would suck. Again, what's the opposite of at least 1? What's the opposite of at least 1 person?
Exactly 0.
Or at least 1 head, yeah. 0. So if I just do the formula for 0, so I can do 1 minus. I'm going to do the opposite and do 1 minus. So 1 minus, I'm just going to cut to the chase. 0.5 to the 14. You get 0.999938. So it says 0.9999. Kind of makes sense. If you flip a coin 14 times and you get nothing but tails, what would that be evidence of?
A weighted coin.
Yes, a weighted coin. Exactly. That's evidence, not proof, because that's not impossible. So the probability to get at least 1 head, if you flip it 14 times, it should be really high. You should get at least 1 head, right? Okay, maybe. And again, if you look down here at, well, at least 1 head. So see the 0, what this means is just above 0% chance. That means all the rest of these should add up to be really close to 1, and it is. It's 0.9999. Okay. So what I want to show you, we just did 2 examples real quick, kind of a little review. What's the mean going to be? Well, if I flip a coin 14 times, how many heads do I expect to get? 7, which is 14 times 0.5, 7. Standard deviation will be that, the square root of all that business.
5 square root of that 5, which is 1.8708.
Yeah. So now we have so if I ask you, when do things start to get unusual? Like, if I flip a coin 14 times, would it be weird to get 8 heads?
No.
Why would it not be weird to get 8 heads?
Because that's just one more than me.
It's really close to the average, right? So this idea of close, I really would it be weird to get 14 heads if I flip a coin 14 times?
Very weird.
Shit, yeah. But somewhere in there's that boundary between not weird and weird. Usual and unusual. And that's what this next thing is. Why did I put a point there, Jeff? I don't know. Make that a part of the circle. There we go. So the mean minus 2 steps, that'll be roughly 3 so that'll be
3.25.
3.2 something. What did you say?
2584.
258, blah, blah, blah. And then the mean plus that, which will be 3.74. So it'll be 10.742, maybe? Yes.
10.742.
I can't see from this far.
Oh, I'm sorry. I am writing kind of small. So if you take the mean minus 2 steps, that's the lower usual number. And if you take the mean plus 2 steps, what did I just say it was?
10.742.
Thanks, man. That's the highest usual amount. So anywhere from 4 to 10, because of course we're dealing with whole numbers here, right? Yes.
Yeah, I was just going to ask that.
Yeah, yeah.
So you don't want to move that.
So would it be unusual to flip a coin 14 times and get 3 heads?
Yes.
That would officially be unusual because the least number of heads you would expect is this. I really want you to see the connection here. The first day I could have asked you, if I flip a coin 14 times and I get 14 heads, would that be unusual? You guys would have said yes. This is just a formalization of what the shit unusual means. You go 2 steps away from the mean. That's where unusual officially starts. I was talking to one group about you're going to define unusual differently in different situations depending on how severe would getting something wrong be. So if you're in a nuclear reactor, you're going to kind of make unusual start a little closer than 2 steps away. You're going to get off your ass when the little needle starts to get towards the yellow. You're not going to wait till it's in the red. I don't know if you guys are understanding what I mean. So I'm going to kind of shrink how far away I let things get. I want things to be really close to normal in a nuclear reactor, right? Okay. So, this is a histogram using all the probabilities you would get if you did the formula for everything from 0 to 14. And somebody tell me, what's the shape of that histogram, roughly?
Approximately normal.
It's approximately normal. Kick ass. Where's the mean? Right in the middle. I love it. And then the spread kind of tells me how quickly it kind of drops off from there, how kind of fat or skinny it is, right? Notice this. If I wanted the probability of 5, visually, would that not be in fact, can somebody tell me real quick, where does this start? What is this and what is this? What is this right here?
4.5.
Beautiful. And what's this?
5.
So what's the area of this rectangle? What's the width of it? 1. And the height of it is this. So this is a quick visual of the probability equals the area. It's another way to kind of think of it. Okay. So we're gonna come back to this question. What's really important right now is the area. If you're given a visual of the probability, the area related to what you're asking equals the probability. Okay. And we've seen that already for a uniform curve, uniform distribution. And then this, let me ask you this. If you wanted to know this area, does anyone know the geometric formula for the area of kind of a slightly melted rectangle? Did you guys learn melted rectangle geometry?
No.
I really want you to understand, is this a rectangle?
No.
Shit, no, right? That's why we need help. If I want to find areas in a curve like this, I can't just do length times width. That's a freaking rectangle. This ain't no freaking rectangle. Part of it is curved. Now, thank God, you don't need me to suddenly teach you calculus, all right? Because one thing calculus does is it helps you figure out the area under something. Believe it or not, that's one huge thing. That's one of two things you learn in calculus. One of two main things is how to calculate the area under something. So let me do two things. Can somebody remind me? In fact, you can look at the picture if you need to. Do you guys remember what percentage should be within one step, one standard deviation? Do you guys remember? 68%. So let me see if you guys can get this. What percent should be below one standard deviation below? What percent should be here? If I go one step down, what percent should be below that? Well, that's 68. How much is out there?
32.
And how much is on that side?
16.
Is that cool? 68 in the middle, 32 total. Cut it in half because it's symmetric. 16 on that side. So it should be about 16% on that side. You guys with me? You're all like, all right. So let me give you this. Don't freak out. Well, if you want to, you can freak out like that. Control.
That doesn't inspire hope in me.
That's a good point. I'll have to
Discourse?
tone down my messaging.
It's like basically an answer.
Yes, I love it. That's exactly how I describe this. This is a sheet with all the answers on it. Now, the first thing to get used to with this table is how the hell to read it. So the very first thing to notice is on this table is a picture showing you when it works. You have to know it's a normal distribution. Let me immediately say this. Do not write any notes or anything on this table. You're going to use this on future quizzes and tests. I'm going to collect it from you, and if there's any notes or anything written on it, you will lose points, right? Does that make sense? Because you're not allowed to cheat. It's crazy. So don't accidentally write some notes or something on there. Okay. If you do, I'll give you a clean copy for a test or a quiz. No big deal. So let's see, how the hell do you read this thing? Notice there's a negative side, positive side. So for this problem we just talked about right here, what's the z-score that I found the area below? Good, 16% below -1. So let's look at the negative z-score side.
Yep.
Here's how to read this crazy-ass table. I want -1.00, correct?
Yep.
Do you see how this table goes out? So if I wanted -3.12, -3.12, this top row tells me the second decimal place. This is how to read this. -3.12, that would be the area below -3.12. We currently want to know the area below -1. So I'm going to look at -1.00. And what is that area?
Pretty much 16.
Yeah, so if you round it to two places, which is really what empirical rule does, you'll get 16%. So negative 1.001587, 16%. And now you guys kind of see why I was making you do all probabilities to 4 places, just so you'd be completely comfortable with this chart. It does every probability to 4 places. Okay, so let's do one problem from the other side, and then we'll call it a day. Yeah, I think that sounds good. There it is. So look at the other side of the uniform thing we just did. This guy. This problem right here. Don't say anything. Well, first off, draw this. What goes right in the middle for a z-score problem? In fact, guys, let me say this. You ready? As a student, what would you love to know about a test I'm going to give you?
Average score.
No. Not that I have given you, that I'm going to give you. What would you love me to tell you about test 2?
How many questions?
Get even more ambitious.
Answers.
Get a little less ambitious. Question. If I told you, in fact, I will give you the answer. I'm going to tell you right now a question I'm going to ask on every test. It will be on every frickin' test. And then I'm going to tell you the frickin' answer. And you actually know the answer. What does a z-score tell you? We've talked about this before.
Nothing away from the standard deviation.
No?
Z-score tells you percentiles, basically. How much data
No.
is below it.
No, it doesn't. Only if it's normal. So z-scores, what do they always tell you no matter what? You got the right words, but the number of standard deviations from the mean to a data point. Let me say that again. I'm telling you the answer to a question that will be on every test. Every other test. Do you understand what I'm saying? And I have yet to get more than like 75% of the students get it right. I always get, unfortunately, most of them get half of the people get it wrong. I'm going to ask you, what does a z-score tell you? And what does the z-score tell you? The number of standard deviations from the mean to a data point. So the way I look at standard deviation is it's how far the tick marks are on a ruler. And a z-score is when I measure something with the ruler, what do I get? So standard deviation tells me the unit of measurement I'm going to use, and the z-score is how many of those are between some things. So if I wanted to know how far apart 2 people were in this room, would I use miles? No. Could I? Yeah, could, but that would be stupid. I would use inches or feet, right? So that's sort of like standard deviation. It tells me what my tick marks are going to be. Z-score is when I actually measure how far 2 things are apart. So a z-score tells you the number of standard deviations from the mean to a data point. And that's why if a z-score is negative, you're below the mean. Z-score is positive, you're above the mean. So so if a z-score is the number of standard deviations away from the mean, what z-score will the mean always have? How far away from the mean is the mean? 0. So where is 1.18?
1.18 above 0.
Somewhere up here. What area am I asking you to find?
The area below it.
Yeah, so I shade that in. Now, take a minute. Don't say anything. Try to find that area on the chart. Like Edmundo said, that z-score table is a collection of all the answers to a lot of the problems we're going to do. All the answers are there. You just got to find them. And by the way, this chart was built using calculus. And to be honest, it was built using a computer, using calculus. So.
It was built by a computer that a human made.
Yeah, human make it. Human make it. Yes, exactly. So am I looking at the negative or positive side? What's my z-score? Is it negative or positive?
Oh,
Okay, so I want to look at the positive side, and I want to find 1.18.
-6 for what? Oh, wait.
1.18. 8810. So there is about 88% of the distribution is below 1.18. So if test grades were normally distributed and your z-score was 1.18, you scored better than 88.1% of the other students. So like Amundo said earlier, z-scores could lead to something like percentiles if you know they're from a normal distribution. So what's the only time you're allowed to use that kick-ass list of blue answers there? What's the only time you're allowed to use it?
Standard normal distribution.
If it's a standard normal distribution, right? So what's a really key thing in statistics then? If I know I'm working with a normal distribution, I've got all the stupid answers. I can just look them up. So a big thing in statistics is, how do you tell if something's normally distributed? So that's going to be one thing we're going to kind of come back to. How do we tell if this is normal? Because if it is, I can just look the answers up. That's crazy. All right, so next time we'll finish this. But that's a good start. So of course, next time is going to happen after spring break. So I hope you guys have a decent break, or maybe even a great break. Don't forget your stuff. Thank you.
No, it's
Oh, okay.